Okay, so we're going to be talking about binomial probabilities right now, and the first part may not make a lot of sense to you guys until we get into the application, okay? So just follow along with me, and hopefully as we go along you'll be okay. So in lesson 10.3 we use the expansion of h plus t to the fifth to find the probability of getting 2 heads and 5 tosses of a pair coin. This is a sample of a binomial experiment. Okay? These types of experiments have the following features. And there's a little typo there. There are repeated situations, and those are called trials. That's the same as what we've had before, trials. And there are fixed number of trials. For each trial, there are only 2 possible outcomes. So in other words, a pass or a fail, or a success or a failure. Okay, that's an important way to be able to tell what you're dealing with, if it's a binomial one or not. Okay, a pass-fail type situation. Okay. The probability of success is the same in each trial. For instance, flipping a coin. If I say heads is a success, what's the probability of flipping for a heads? 0.5, okay? So if it's 0.5 on the first trial and I flip it again, does it change the probability of landing on a heads? No. So that's an example, because it's either you pass or you fail, and it's the same probability with each trial. Okay? The trials are independent events. Flipping a heads or tails does not make any difference on the next trial. It won't affect it at all. So it's independent. So listed below are all the possible outcomes for a binomial experiment with 4 trials. Okay? So say we flip a coin 4 times. 4 failures, the possibility of getting 4 failures on this, there's only one way for that to happen. Only one possible combination. Okay? The possibility of getting 1 success are the following ways. You could fail 3 times, then succeed. You could fail twice, succeed, and then fail. You could fail, succeed, and then fail twice. Or you could succeed on the first try and fail the rest. Do you guys see how they're getting at these? Okay. So, yeah. So that is how they're coming up with all these possibilities, number of outcomes. Okay? Notice that if you use the combination formula, you can come up with a number of possible combinations by using this. We have 4 trials and then get only no successes, 1 success, 2 success, 3 success, or 4 successes. Okay? Okay. So moving on. So example 1A. Suppose that the probability of a heart pacemaker working flawlessly for 1 year is 0.85. What is the probability that 2 patients out of 4 receiving pacemakers this week will have some kind of problem with their pacemakers over the next year? Okay. So, first of all, we need to look at the probability that the pacemaker is working flawlessly. So what was that? 0.85, okay? We're going to call that P, little p. All right? Now I want to look at the probability that there's a problem. Okay? So what would that be? 0.15, you just take 1 minus the success rate, right? So it'll be 0.15. And we're going to call that little q. Right? Okay. Since there are 4 pacemakers, there are 4 trials. All right, does that make sense? We want to know success, failure on all 4 pacemakers, so we'll call them each a trial. Okay. So based on the fact that there are 4 trials and we want to see if there are 2 patients out of 4 having issues, we're going to go up here and look at this one because that would be 2 out of 4 successes. So do you guys see why I picked this column? Okay. All right. So,
Wait, no, why did you choose that?
because there are 2 successes and 2 failures in each of these combinations.
It's just because it's half and half.
Yeah. So we need to make sure there's at least 2, or only 2. We're just looking at only 2, actually. Okay. So the probability of each of these outcomes is p squared q squared. Okay. So the probability of the pacemaker working flawlessly, 0.85 squared. And the probability of it not working well is 0.15 squared. All right? And we also are going to take this number right here and multiply it times this to find the actual probability of 2 successes. Okay? So, the probability...
Wait, hold on. How do you know that it's 0.15 is Q?
Because Q is the problem with the problem, the probability of a problem.
Oh, that's all that's left.
Yep. So the probability of exactly 2 successes in 4 trials. You're going to find the number of possible combinations. We found it up on the chart. It's going to be 6 times our probability of just p squared q squared. And that's going to be times 0.85 squared and 0.15 squared. 6 comes from up here. We know that we're picking this one this column right here. And there's 6 possible combinations or arrangements of it. If you put this in your calculator, it comes out to be about 0.0975. And if you round that up, it ends up being about 10% chance of having 2 of them fail in the next year. I'll move that up so you guys can see it a little better. All right, some hereditary diseases are inherited by 1/4 of all the offspring of families in which the hereditary gene is present. In such a family has 4 offspring, what is the probability of exactly one of the offspring inherits the gene? This is actually a close to home situation for me because I carry cystic fibrosis. So does my husband. So, cystic fibrosis is a disease of the lungs and also the intestinal tract. So what happens is a person that has cystic fibrosis tends to make way too much mucus, and they can end up drowning, basically. By the time they're 18, they have to have usually a lung transplant. Yeah. All right, so what we want to do is if such a family has 4 offspring, we want to know the probability of exactly one having the disease.
25%.
Okay, yep. So first of all, we can use, I just want you guys to know, we can use the table that we used before, which is on the page before, okay? Okay. So let's find the probability of not having the gene. Yep. So that would be 0.75, okay? And so Q, the probability of having the gene,
Wait, do I want to do P?
you could say P and then call it Q. So this would be P, right?
Why is it
That's just what typically in math they use.
So is P always no and P says yes?
Yeah, typically.
Are we
Yeah.
gonna have a copy of the table on the
No. So this would be 0.25. So that would be Q. All right. All right. So we want to look at 3 successes, right? We want to have 3 of the children be successfully not having the gene. Okay. Look at. Pardon me?
Oh, this is like stuff we did in bio.
Yeah. Yeah.
It's like those boxes.
Exactly. Okay. So look at 3 successes. So let's go back to our table and look at where our 3 successes are. They are right here. 3 successes, we're going to use this right here. So what is our coefficient for that? 4. Okay. So we want to find the probability of this. It's going to be probability of having only 1 with the gene, okay? So that would be P of 3, well, we're going to times 4 times P of 3, Q of 1, correct?
Oh yeah.
Okay, so 4 times 0.75 to the 3rd power times 0.25 to the 1st power.
So every time you have
The probability is 0.4219. So that means it's a 42% chance of having 1 kid have the gene.
that was for you too.
Out of 4.
You had almost like a 50%.
Okay, so we are going to be looking at an activity that I'm going to do with you right now. We want to compute the probability that 2 or more pacemakers have problems during the year. Okay? So in order to do that, what we really need to do is find out the probability of 2 having a problem. Okay? We already did that one. But we also need to find the probability of 3 having the problem, and then 4 having the problem, and add them together. Okay? So that's what you do when you have something that says 2 or more. All right? So let's first of all look at the problem of 3 having a problem. Problem of 3 having a problem. Okay, so if 3 are failures, that would be like this one right here. 1 success, 3 failures. So it's got to have a coefficient of 4, correct? Okay. So, oops, did I go too far? Yep.
Write the probability.
For 2 shooting.
Yeah, that should be right here. What was that again?
Like
10%.
It was, yeah, 10%, right? Or 0.097, I think.
0975.
Okay. Okay. So at 3 having the problem, we have a coefficient of 4, and it's going to be P to the 1 of being successful, right? So it would be 0.85 to the 1st power and 0.15 to the what power? 3, okay? And the probability of all 4 of them being a problem, the coefficient for that was what? 1. And then this will be 0.85 to the 0 power, which what happens to that? It goes away to a 1, right? And then this will be 0.15 to the 4th. Okay? So if you add all those together, you end up getting 0.1095, which ends up being close to 11%. 11% of having 2 or more. Okay, so in general, just so you guys can write this down, exactly K successes, we just experienced that. If you have N trials and you want K successes, your formula would be P to the K and q to the n minus k.
Wait, is that all
All
one thingy?
one thing.
Yeah,
Does
so it's multiplying.
Okay, times.
Okay?
Is it n minus k or n minus q?
Oh, k, sorry, that should be k. There should be a k right here, guys. All right, so that's it in general. But let's try number 2. Suppose a quiz has 10 multiple choice questions, with each with 5 choices. If a student guesses randomly on each question, what is the probability the student will get 7 or more correct? Now we mean randomly. They're not actually reading the question and trying to figure out the answer. They're going through and making a Christmas tree or something. You know, it's just, they're not even thinking about it. Okay? So, in this case, we have n equals 10. That's the number of trials we have. The probability of a success is what? How many multiple choice? 1 out of 5, right? We have 5 possibilities for each question. So the probability of success is 1 out of 5. Okay, so this would be 0.2 in decimal form. Okay? The probability of a failure would be what?
4/5.
Yeah, 4/5 or 1 minus 0.2, which would equal 0.08. 0.8, yep. Okay? So we want to know what is the probability that a student will get 7 or more. So P of 7 or better is going to equal P of exactly 7 plus P of exactly 8 plus P of exactly 9, and so on, right? Okay? So, let's figure this out. P of exactly 7. We're going to use the C values to find this because we don't have it on the board. We don't have our Pascal's triangle all the way down. So if you had it down to row 7, you could do this. Actually, it has to be row 10, right? 10 trials. But so we're going to write it out like this. 10, 7C times, okay, the probability of having success is 0.2 to the 7th power. Probability of failing at this point is to the 3rd power. Okay, 7 plus 3 is 10. So we got to make sure that those powers are adding up to 10. All right, the probability of at 8 is going to be like this. 10C8 times 0.2 to the what power? 8th, and 0.8 to the 2nd. Good. And then we'll have 10 choose 9 times 0.2 to the 9th, and then 0.8 to the 1st. And then lastly, 10 choose 10. Okay, I'll be 0.2 to the 10th. Why did I not bother putting 0.8 to the 0? Just goes to 1. Okay. So remember, 10 choose 7, that would be the same as me saying 10 times 9 times 8 times 7 times 6 times 5 times 4, all the way down 7 slots, right? 1, 2, 3, 4, 5, 6, 7. There you are. Then 7 times 6 times 5 times 4 times 3 times 2 times 1. And 7 through 4 cancel out. This is from before. So this is just a review. So that would be the coefficient for that one.
So what does this equal?
So it all in the end it equals the following. It ends up being 0.000864.